As we learned the symbols for the proper subset and the general subset in the last section, it may have reminded you of something that you already know about inequalities. So in section 2.2.3, we're going to associate inequalities with our subset symbols. Let's look at how what we know about inequalities will help us to understand subset notation. The first table that you see there deals with inequalities. On the left side, we have our two inclusive inequalities. They are less than or equal to and greater than or equal to. Those are really two symbols in one. They're expressing an inequality and also the possibility of an equality. So for example, 5 is less than or equal to 5 is a true statement because it is satisfying the equal to part of that sign. So that inclusive inequality symbol allows for the possibility that the two elements on either side of the symbol are equal. In contrast, we have two strict inequalities. They are less than and greater than. They do not allow for the possibility that the two elements on either side of that symbol are equal. So 5 is less than 6 is true because 5 is strictly smaller than but not equal to 6. That is the most specific expression of the relationship between 5 and 6, but we could also say that 5 is less than or equal to 6 is also true. Now, this is how our subset symbols work. Our general subset symbol indicates that the set on the left may be smaller than or equal to the set on the right. For example, the set 1, 2, 3, 4 can be expressed as a subset of the set 1, 2, 3, 4 because it satisfies the equal to part. Specifically, it is expressing this part of that relationship. Those two sets are equal because they have exactly the same elements. Our proper subsets are much like our strict inequalities in the fact that they indicate that the set on the left must be smaller than the set on the right, and it excludes the possibility of equal sets. For example, the set 1, 2, 3 is a proper subset of the set 1, 2, 3, 4 because the set 1, 2, 3 is smaller than the set on the right. But even though that is the most specific expression of the relationship between those two sets, the general subset symbol would also be true. So if you can associate this new information regarding subsets and proper subsets with what you already know about inclusive and strict inequalities, it may help you to understand a little bit better. In example 5, we're going to practice all of these symbols plus our roster notation and our set builder notation by determining if the following statements are true or false. Example A. The set 2, 4, 6 is a subset of the set 1, 2, 3, 4, 5, 6. Notice every element in the set on the left is also an element of the set on the right. So this is a true statement. The set on the left is a subset of the set on the right. In the next example, we have the set 2, 4, 6 again as a proper subset of the set 1, 2, 3, 4, 5, 6. This is also true. This is a more strict expression of the relationship between those two sets. It's more specific. And in example A, it allowed for the possibility that the two sets are equal, but does not require it. Now, as we go through these examples, if you want to pause the video and go through these problems, determine if they're true or false, and test your intuition, and then restart the video and check your answer, that would be a great idea to see how you understand so far. In example C, we have the set MATH as a subset of the set HAMT. Notice every element of the set on the left is also an element of the set on the right. However, this is expressing a proper subset relationship. So that means the set on the left must be smaller than the set on the right. So this statement is false. Be careful with examples D through G. There's little subtle differences in the notation that affect how we make our conclusion. Remember, every single mark in mathematics is efficient and dense, and it expresses important information. So example D says Texas is an element of the set containing New Mexico, Colorado, Oklahoma, and Texas. Remember, this is our set membership symbol. It says Texas belongs to that set, and that is true. Notice on the next example, it says Texas is a subset of the set containing New Mexico, Colorado, Oklahoma, and Texas. This is actually false. Now, you might be thinking, well, Texas is an element of the set on the right, and it is a subset. But notice on the left side, it is expressed as an element. It is missing curly braces. So what we have on the left here is an element, not a set. That's corrected in example F. Notice in example F, we have an actual set over here. Only a set can be a subset of another set. So the set containing Texas is a proper subset of the set containing New Mexico, Colorado, Oklahoma, and Texas. That is true. Proper subset is appropriate because the set on the left is smaller than the set on the right. And example G, we have the set containing the single element Texas as a general subset, which allows for the possibility of equality but does not require it. It's a subset of the set on the right. That is also true. How you doing so far? Some of these subtle differences can really trip you up, so you got to look at the details. Example H. The set B is an element of the set containing A, B, C, D. Now, look carefully. I see a B over here, and I see a B over here. I see there is some relationship, but this is expressing element set membership, right? The set B is not an element of the set A, B, C, D because the structure I have on the left here is a set, not an element. So that is false. Look how this is changed in example I. Still have my set symbol over here, and I'm still using the set membership or element symbol. But now notice that every element of the set on the right is also a set itself. So this is true. That is, this is an element, an identical element that I can identify in the set on the right side. Are you wondering, where did all the numbers go? Where are the equations and graphs? What does this have to do with math? Well, these foundational logical principles are how we handle things like solution sets, or even a graph can be expressed as the set of all solutions to a two-variable equation. So these are fundamental principles in math, and maybe you've never seen that connection before. Example J, the set QRS is not a subset of QRS. Remember, that symbol has the equal to part, so it is allowing for the possibility that those are equal, but it is negated. So this is a false statement. If I wanted to make it a true statement, I would get rid of the slash on the subset symbol. Example K, the empty set is an element of the set containing VIOLA. The structure we have on the left is a set, not an element. So this is a false statement. Example L, the empty set is a proper subset of the set containing VIOLA. This one is true. The structure on the left is a set, so it can be a subset. And in fact, the structure on the left contains 0 elements, where the set on the right contains 5 elements. Since the set on the left is smaller than the set on the right, it is in fact a proper subset. And remember, the empty subset is a proper subset of every set. Example M, 0 is an element of the empty set. What do you think? True or false? This is false. This is indicating that the empty set has an element, and we know the empty set is empty. It has no elements. The last example, 0 is not a subset of the empty set. That is true. The only subset of the empty set is the empty set. So 0 is an element. It is not a set. Therefore, it cannot be a subset of the empty set. All right, your brain may be in a tangle. This is going to take some practice, so we'll see some more examples in the next video.